Hello class, welcome to this lesson 6.1. We're going to be discussing the normal distribution. So this is the lesson where it starts to combine the statistics and the probability lessons in one. So we're going to start combining the concepts of both probability and statistics. Alright, so what is a normal distribution and how can we find the area under the standard normal distribution curve? So the goals are to be able to identify the properties of the normal distribution and find the area under the standard normal distribution given various z values. So we're going to be talking about the normal distribution, the standard normal distribution, and the empirical rule. So remember in a previous lesson, we looked at probability distributions as a whole. So we looked at discrete and continuous probability distributions because those are the two types. And we mentioned that discrete means usually countable whole number values. For example, the number of sixes rolled from dice. And continuous means that it's usually measurable whole number values and all the numbers in between them, like decimals, like such as weight, height, etc. Now, one example of a discrete probability distribution was the binomial distribution, which was in 5.3. Now we're going to actually discuss an important continuous probability distribution, the normal distribution. So the normal distribution, if a random variable has a probability distribution whose graph is continuous, bell-shaped, and symmetric, it is called a normal distribution. The graph is called a normal distribution curve. Now the distribution is also known as a bell curve or a Gaussian distribution curve. So below is a picture of Carl Friedrich Gauss. He was the one whose name the distribution curve is after, so it's named after. And this guy is a math prodigy, and he was able to come up with the equation of the curve. He's also known for a lot of things, such as in physics, contributing to electricity and magnetism. In fact, there's an actual unit of magnetism that's named after him, which is the Gauss, interestingly enough. So the equation that he came up with for the normal distribution is given below. So it's an exponential function, e to the negative x minus mu squared divided by 2 sigma squared, and the entire exponential divided by sigma times square root of 2 pi. So some of these variables you may be accustomed to, and some of them you may not, depending on your level of algebra. So x is just going to be the variable that we're used to here, that we use for any distribution. And remember that mu is the population mean, which we discussed in in one of the earlier chapters. Like I mentioned, we are introducing statistics in here as well. And then sigma is the population standard deviation. So you probably remember those two things. Now you probably also remember pi, which is 3.14. So it's very interesting that something, as interesting as pi is actually in this formula, because pi appears in a lot of different formulas, even though it's related to a circle. And then e is another constant that you may or may not know, and that's a constant of exponential growth. Now you're not going to need to know this equation. This is just simply to let you know that all curves have essentially a mathematical equation, and we're going to go ahead and use this equation to graph and show you how the normal distribution looks like. So right here, we're going to go ahead and show you a demonstration of the normal distribution function using that equation, the Gaussian equation. So if you look here, I actually plugged in the Gaussian equation, and I used m instead of mu and s instead of sigma for the standard deviation. But if you notice, it looks like a standard bell curve. And notice that if I take this mu equals 0 and I change it to mu equals 1, that the normal distribution actually shifts to the right. And if I change it to -1, then it shifts to the left, as such. Now I'm going to go ahead and leave it back, return it back to 0. And now I'm going to change the standard deviation. Remember that the standard deviation is a measure of spread. So if I change this number, it's going to change the spread. So if I increase this number, it's going to increase the spread. So if I increase it to a value of 2, notice how flat that normal distribution actually looks like. So if I zoom out, it's still a bell curve, but it's actually very, very flattened, if you will. Now if I decrease this value to say 0.5, then the curve actually peaks, and you can actually see the peak there. And that's because it's less spread out, and so therefore it's more clumped in the middle. So remember, the standard deviation is a measure of spread, so if that value is low, the graph is not very spread out, it's actually more clumped. And the mean is the measure of center, which tells you where the center of the graph is located. And so if I change that center, then it changes the location of the graph. So hopefully you were able to get the 2 bullet points from this. The main key properties here so far is that the position of a normal distribution curve depends on the mean parameter. The shape of a normal distribution curve depends on the standard deviation parameter. So recall that a large standard deviation means a larger spread, which means a flatter curve. A small standard deviation means a smaller spread, which means a more peaked curve. And there's an image below of how this looks like. So if you remember, if I change the mu from 0 to 2, it shifts it to the right. If I change the standard deviation and so that it's bigger, then the graph actually flattens out more. All right, so now we're going to actually look at the properties of the normal distribution. So first off, we have the first property is that the normal distribution is actually bell-shaped. And you can clearly tell that this is the case. It has the shape of a bell, and therefore we call it bell-shaped. Now the second property is that the mean, median, and mode are equal to each other, and they're located at the center of the distribution. So basically the center of this distribution, we said that that was the mean, we called it mu, but that's also equal to the median, which is also equal to the mode. And remember that the mode is the most popular number. So in this case, it makes sense that the peak is the most popular number because there's more of that number. Now the third property is that a normal distribution curve is unimodal, which means it only has the one mode, which makes sense because we only have one peak here, and therefore it's only one mode. The fourth property is that the curve is symmetric about the mean. So you can kind of tell if the mean is in the middle, then it's symmetric on both sides of the mean. Now the fifth property is that the curve is continuous. There are no gaps or holes. In other words, I can trace this curve without ever having to lift my pen or pencil, and therefore it is called continuous. Now the sixth property, it actually helps to actually demonstrate this on Desmos. So the curve actually never touches the x-axis. So let's go ahead and show you again the Gaussian function by writing the equation using the same demo as earlier, but this time we're going to focus on the x-axis. So notice that we have the x-axis and the curve continues, and goes forever in both directions. Now at this point, it looks like the curve actually touches around the 4 mark, right? But if you zoom in and you actually zoom into that curve, and you zoom in and you continue to zoom in, notice that the curve actually never touches. And then as you continue to go on and on, the curve still never touches. And it actually goes on forever. And even when it looks like it touches, you can always zoom in further and find that it actually doesn't touch. So this is a very interesting property, and this actually works on both sides of the bell curve. This actually works on the negative side as well, where you can always zoom in and you find that it never actually touches or crosses the x-axis. So property 6, the curve never touches the x-axis. Now property 7 and 8 involve the area under the curve. So property 7 is the total area under a normal distribution curve is equal to 1 or 100%. you can imagine that this is a very interesting property, which is why we use this in applications of probability. Because remember that the total probability of any given event should equal 1 when you add up the probabilities. Now, the area under the part of a normal curve that lies within one standard deviation of the mean is approximately 68%, which is given in the curve above. So if you look at here, this is the mean in the middle. And notice that this says that this is mu plus 1 standard deviation, mu minus 1 standard deviation. So we're going 1 standard deviation on each side. So we're going 1 sigma on each side, plus or minus. Now, if we're going within 1 standard deviation on each side, well, each half of the curve is 34%. And so the entire curve is worth about 68%. So basically, the area under the normal distribution curve, when you're going from 1 plus or minus 1 standard deviation on each side, is going to be 68%, always. Now, if you're talking about 2 standard deviations on each side, then here we're interested in 2 standard deviations on each side, which means we're going 2 sigma on the right and minus 2 sigma on the left. So within 2 standard deviations on each side. And then notice that if we add up these probabilities, we get about 95%. What about 3 standard deviations? If we do 3 standard deviations, then we're going to basically increase this part all the way to 3 sigma and minus 3 sigma, and we're covering more of the curve. So at this point, it looks like we're covering almost 100% of the curve. And in fact, if you add up the probabilities within 3 standard deviations, you get almost 100%. In fact, 99.7%. And this is actually, this rule right here, and this always works for any type of normal distribution. Now, this rule is known as the empirical rule. So it's a very special rule, and we're going to be using this rule at some point, and we're going to be interested in these specific percentages at some point. So it's important to know that there is not actually one normal distribution, because remember earlier that we mentioned that there are a few different normal distributions, right? Depending on the position of the shifting of the curve, right? You can have a normal distribution with a mu of 0, or a normal distribution with a mu of 2, or with a different standard deviation. So there are different spreads or different shapes in which some are spread, some are not a spread, or positions of normal distributions that you can have. So therefore, because there are a bunch of them, and we can shift and stretch them in different ways, we want to basically take any normal distribution and collapse it into one distribution in order to make calculations simpler. And in this case, we have one distribution that we use often, and that is known as the standard normal distribution. Now, the standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. So this was actually the normal distribution that I presented to you earlier in Desmos. That was the very beginning one before I shifted it. So if you want to take a look at it, we mentioned this. So this is the standard normal distribution. Notice that the mean middle starts out at 0, and that the spread is 1 each time. So the standard deviation here is equal to 1 because it's spreading by 1 each time. The equation for the standard normal distribution is given here on the bottom right. All right, so the standard normal distribution is used to simplify all situations involving different normal distributions. In practical applications, we want to convert the normal distribution into the standard normal distribution in order to make calculations simpler. Now remember that I presented to you the equation for the standard normal distribution earlier. Now the question is, what is that z in that formula? Well, you may recall that the z is actually the standardized score, or the z-score. This is back from lesson 1.9. The z-score, if you recall, is calculated by taking the value, in this case the x value, minus the mean divided by the standard deviation. So this is the formula for the standardized or z-score. So the purpose of the z-score is to convert each value of x from a specific normal distribution and convert it to a z-score so that the z-score can be used for the standard normal distribution. So basically you can take any x value and convert it to a z value in order to make the calculations simpler when we do problems in the future. So the z value or the z-score is actually the number of standard deviations that a particular x value is away from the mean. So we want to find areas under the standard normal distribution curve. So in problems involving normal distributions, we're often interested in finding this area. The reason why we're interested in finding this area is because recall that the property of normal distributions was that the area under the normal curve is actually the probability of a population with a given characteristic. Remember that one of the characteristics of the normal distribution is that the area under the entire curve is actually equal to 1. And that was a property that was very interesting for applying it to probability. So we want to find the area in order to find the probability of a given event happening, or the probability of a population having a certain characteristic. So how do we find the areas under the normal curve? Well, step one, we want to draw the normal distribution curve and shade the area that is desired. Step two, you want to find the appropriate figure below and follow the directions given based off of the direction of the area that is being shaded. So if you are looking for an area to the left of the z value that you're going to shade, then you need to look up the z value in the table and use the area given. So that would be under case 1. If you're looking for an area to the right of a given z value, that would be case 2. And then you would have to look up the z value and subtract the area from 1. If you're looking for the area between two z values, that would fall under case 3, and you would simply look up both z values and subtract the corresponding areas together. Now, what is this z-table? The z-table below actually gives you the area under the curve to the left of any z value that is given. So notice that you have the normal bell curve, the bell-shaped curve here, in that the area is shaded to the left. And that indicates that the table is only giving you areas to the left of a specific z value. So basically this is a chart that you can always reference, and that is a very common chart. So if you look up a z value, let's say you're interested in a z value of 2.28. Z equals 2.28. And you want to find the area to the left of that z-score. Well, then you're going to look this up in the table. So you're going to go to positive, these are the z-scores here. So you got positive 2.28. So positive 2.28, because that's your decimal, 2.28. And then between those, you will locate your area. In the case the area is 0.9887. So in this case, the area for z equals 2.28, the area to the left of that, which we'll call P of, we'll call this P of z is less than 2.28. This indicates that we're looking for the area or the probability of the curve to the left of z equals 2.28, where this value is 2.28. And that area is, we said that it was 0.9887. So this is an example of how you would actually use the z-table to find areas to the left of the normal distribution curve. All right, so we're going to look at some examples for the next few slides here. So for the first example, what if we want to find the area under the standard normal distribution curve, where in this case they give us P of z is less than 2.09. So what does this actually mean? Well, first off, this actually means that we're looking at the area to the left. of 2.09. So that less than value means we're looking at the left. So let's look at step one then in that case. So step one, we're going to be drawing the normal distribution curve. So this is the normal distribution curve drawn here, the standard normal distribution curve rather. And we have the value of z equals 2.09 labeled, and we want the area to the left, which is shaded in red. All right, so since we want to look up the area to the left, this is the first case in the steps mentioned in that slide, in the previous slide. So we want to look up the area in the table in the z table. So we're going to go ahead and look up the area in the z table, and that will be our answer for this question. So we want to look up the area to the left of 2.09. So here we got the negative z values, and we want the positive z values. So we're going to go to 2.09 in the positive direction. So we have 2.09. So then we want to basically figure out where they both cross. And we're interested in this probability, 0.9817. So our probability here is 0.9817. So this means we basically got 98% of the curve, which is the area underneath this curve. All right, so now let's say we want to find the area under the standard normal distribution curve, in which case we have P of z is greater than negative 1.14. So in this case, we're looking at a greater than symbol, which means we're looking at the area to the right of that given value right there. So if we wanted to do step one, well, we're going to go ahead and draw the normal distribution curve with negative 1.14 on the left side. We want to shade the area to the right. So next, since we're looking at for the area to the right, which is the second case, we need to look up the area for negative 1.14 and subtract it from 1. Why is that? Well, remember that the table gives us the area to the left by default. And so if we want to get the area to the right, well, we know the entire curve is worth 1. So if we do 1 minus the area in blue, well, that gives us the area in red. So that's the idea of why we need to subtract from 1. And this is demonstrated here. So P of z is greater than negative 1.14 is equal to 1 minus the probability that it's less than. And remember that this is the area that's given in the table. The table gives us the area to the left. So we're going to go ahead and look up those values, or the value of negative 1.14. So we have negative 1.14. And so we go ahead and trace those values, find out where they intersect, and we get the area 0.1271. So now that's only giving us the area, remember that's only giving us the area to the left. So if we want the area to the right, we got to do 1 minus that area, right? So 1 minus 0.1271, and that will give us the area to the right. So we're going to do that over here. We have 1 minus 0.1271, which is going to be 0.8729. Which, according to this graph, makes sense. We seem to have, at least 80% of the curve or more actually shaded. So this makes sense. All right, let's look at the last example. So let's say we wanted to find the area under the standardized normal distribution curve between these two z values. So here we're looking at the curve between two z values. So in order to do this, we're going to be drawing for step one. We have those two z values labeled, and notice we shaded between them. Now for step two, we're interested in the area between two given z values, which means we're looking at the third case. So we're going to look up the areas to both z values and then subtract them. from each other. Remember that you want the bigger area minus the smaller area. So this is shown over here. So we want the probability between two z-values, which means we need to subtract the probability of the bigger one for less than 1.62 minus the probability of the smaller one. And then we look these both up in the table. So we're going to go ahead and look both of these values up. So let's say we want to do 1.62. So we're going to go to 1.6, 2 over here. So we're looking at 0.9474. Now let's look at negative 1.35. So negative 1.35 here and here. They seem to both cross at about 0.0885. And now we're going to simply subtract those values together to get our final area. And you're going to get 0.8589. All right, guys, that's it for the video. I hope you got something from this video. I hope you learned a few things, and I will see you in the next one.